Okay, hello everyone. Today we're going to do the USACO Gold 2022 Open contest. So you guys will see how the contest goes for me, and what it's like to solve the problems. Um, Obviously, Open is usually the hardest contest, so it'd be reasonable for Gold and Open to be reasonably difficult. But let me share my screen and we'll get started real quick. Okay, so we will start the contest and see how it goes. Let's do this. All right, so we have three problems. Apple catching is the first one. So I'll let you guys take almost read it while I read it as well. Hmm. Okay, so this problem statement's actually pretty short. It honestly also feels like it feels like a common like problem scenario too. I definitely remember USACO problem about cows catching apples before. Um, However, okay. So you would like to match up the cows with the apples in some way that allows you to maximize the number of apples caught. The thing I noticed, the bounds are pretty high. So even though you could actually run like a matching algorithm on this, that would probably not work. Um, there might be some sort of greedy approach or processing them in from like a certain order on X or a certain order on T. We'll come back to this problem. I just want to read it. Okay, so this is the second problem. Hmm. So we're given like these sequence of expressions where you can multiply by a digit or add a variable. And you would like to know the number of ways to interleave Bessie and Elsa's programs such that they produce the same result. Um, yeah, we'll need some time about that. And then the third one, we'll get a chance to read all three just to make sure we know the ideas and pick the one we like. Want to start with? So we want to assign values to the tree such that pairs of ancestors, like j being ancestor I, minimizes the maximum absolute difference. So maybe this is some sort of like tree DP. Bounds up to 10 to the 5. It's a rooted tree. Okay. I don't know which one I want to start with. Actually, I might start with balancing a tree. Okay. So let's take a look at one of the samples and try thinking about this. In this case, the first sample. Okay, so this line is the parents. I guess there's, oh, so they split up the test cases. So you don't always have to output the actual assignment. Okay. I guess that makes it easier. I'm just drawing out the sample and then we'll take, or at least one of the samples. Oh, I drew it wrong. Okay. Okay, so this is one of the samples. Maybe we do some sort of DFS over the tree where we keep track of like, well, one idea I would immediately think when looking at this is, can we binary search for so if we knew the maximum distance d, is it easier, right? So this sort of like, if it's then we might want to binary search. So in this case, let's say we're checking this with like d. In this case, the answer is 3. So let's see, can we see if 3 works? Well, maybe we pass down like 0. So like we don't have to assign the root yet. We know when we, okay, so if we pass down 0, 100, we're looking at 1, 1. So you know they're 3 apart. You know, well, there's only one place to place this, so it has to be 1. So like the possible valid range here is 1, 1. I guess the same thing happens here. The thing is, like, like once you've chosen this, something has to go back up the tree. So it seems hard to DFS down the tree. Okay. Another thing we could do is actually do like a bottom up DFS, but I don't know what you store. So in this case, we did a bottom up DFS. Maybe we can draw out the same sample. Let's just copy it. You could pass up the 1-1 and the 6-7. So for the leaves, I guess the range that I guess what are we storing? Do we store the range of the value in a subtree? That wouldn't work. We might want to store like the possible range in each subtree. So like the minimum value and the maximum value. Things we don't know the exact values. Do you store like the minimum possible value? I guess in this case, maybe if you pass up 1-1 and 6-7 in your DFS, you would then be looking at 0-100. You know that you need them to be 3 apart. So let's say we fix D to be 3. Then we're looking at 6-7, 1-1. And we know we can pick the 6 on the right, so we want to pick 3 for the top one. That works since we see the distance is 6 apart. And since it's not more than 6 apart, that's valid, I guess. I don't know. But we don't want to store just a single value, right? Because this only I mean, we store the range of possibilities, but that's not really that useful because the minimum could be restricted to some range, and the maximum could be restricted to some other range. One observation is checking validity of an assignment only depends on minimum and maximum values chosen in each subtree. Reason for this is if we're looking at like SI minus SJ, this is maximized when either SJ or like, let's say SJ is the ancestor, so SI extremal values will give the maximum. So I guess one idea we can do we do like bottom up DFS, but we would pass up a range on the minimum and maximum. So in this case, we're gonna pass up two values, or not two values, two ranges. So in this case, the minimum will be within this range. So we'd pass up like 1-1, 1-1, 6-7, 6-7. And since the minimum has to be within 6-7, 1-1, we know that more extreme version is the minimum of those, because those ranges don't overlap. So we get like the minimum must now be within 1-1, and the maximum must be in 6-7 still. Yeah, I guess. And then you can look at the max value for the minimum and the min value for the maximum. I don't know. Pass up two ranges. What does this look like on another sample? Let's try the other small case. There's another sample. 10. This sample. 0, 10, 0, 1, 9, 10. So we could pass up like 0, 1, 0, 1. So then the minimum would have to be within the range 0, 1. The maximum would have to be in the range 0, 9, 10. Well, there is a value in 0, 10 that is between those. I guess another idea, we only need the for the maximum possible minimum and the minimum possible maximum. So in this case, we could return like the maximum possible minimum is 1, the minimum possible maximum is 0. So pass that up. And here we would pass up 10, 9. And we merge this together, we would take the minimum, the maximum possible minimum would be the minimum of the subchildren's maximum possible minimums. So this would give us a maximum possible minimum of 10 and a minimum possible maximum of 9. Wait, no, I just did that wrong. Maximum possible minimum would have to be 1. Minimum possible max would be 9. Which, because there is a value that this has a value that is also d away from both endpoints, that seems valid. I guess the issue is some of the intervals will have like, if you LR, L can be greater than R, and that's fine. That just I don't really know what our conditions are going to be. Okay, so I guess this idea sounds plausible. I don't really know how you do the assignment because that would not make it easy to drive the assignment. Maybe when you get to the top, you know the possible range. Well, we're not even storing possible ranges. We would at each node check to make sure there's always a choice available. And if none of them failed, then you would return true in the end. But I don't know how you get the assignment yet. We've binary search over this. We check if each one's valid. Maybe this would help us. You know, it's probably worth trying to go for that first before. I don't know. I don't know how we get the assignment. So maybe we'll try coding that. I don't know. We should also try figuring out some other problems. I don't know. I kind of want to code that. At least try it. Okay. Let's start. We have some number of test cases. And this is the size of 3. Parent max n is 10 to the input. I guess we have to store B. So we need to store the range for each node. So that is all the input. Another thing we might want to build access to children of each node. DFS. I'm going to 0 index. Children vector. I guess I also forgot we need to should be 1 index. I guess we need it. We need to clear children. Okay, so what am I gonna want to do with DFS? Some node. We'll make it return the range. Base case. I guess in this case, if we're going with the strategy of returning like the maximum possible minimum, the minimum possible maximum, we'd want to return left of u, sorry. U. Right, that's not what they're doing. Let's say we're checking a specific value of D. We need to keep track the range for all the children. We'll just make this equal to DFS. Not really union again, but so we have range will be DFS children U ID equals, we want the maximum possible minimum, but we already know, so it's the minimum of the maximum possible minimum. So it's the min of our current one, and then our first. I think that's what we expect. So If they're too far apart, then it definitely can't work. Which is a variable. CH range dot first is less than CH range dot second. CH range second minus greater than 2 times D. Valid is false. Well, that's the only case it can fail though, because like I have to keep in mind, still need to check. And we also have to modify CH range. CH range, so the maximum possible minimum would have to be, we now can't be bigger. Ranges of U dot second, right? Because that's the upper bound on this node. So you definitely can't, if that one's smaller than what we currently have, it has to be smaller. We also have to be. Like that, you have to be smaller than. Maybe, okay, I mean, that we're gonna try debugging this. Should be symmetric. Plus D minus, I think is what I meant. Okay, so we'll try. Let me see what this outputs. And we get an index out of bounds. Oh, 9. Oh, we need to just do this for. I guess we want DFS. Let's test this with 0, and let's just say we're doing the first sample. So this is 3. Wait, why do we have multiple outputs for 0? Oh, because multiple use cases. Yeah, 197. That doesn't seem right. So on. Okay. First plus, I feel like this is wrong. I'm not really sure. Well, that does look more accurate because you can't Well, 1, 6. Yeah, yeah. So accounting for the value of D, that did work. Okay, because we didn't want to be 7. Then that might work. I think what we want to do, we're still not done with this function. We haven't checked for intersection. Check this with value. Value equals true DFS. 0 D. Let's quickly implement a binary search. So since I don't know the maximum, I'm just gonna do this trick. Two. So search. We get something. I guess it'd be nice to see what we were checking. Why does it up at 0 for this test case? Okay, so we see 5, 5, 5, 5, 5, 5. So that makes sense. Yes, because you're restricted to 0 and you're checking 5, 5, but this one should not be 5, 6. That should not be valid range. The minimum possible. Oh, that is not, it's not valid. Okay. This is probably wrong again. So we want that to be 5, 5. Maybe this is supposed to be. I guess you can't get that much. You can only shrink by at most D. It's not good. Let me comment out this. Still not the correct range. Because we want it to be the minimum possible maximum. Are these directions switched? Oh, we want the min maximum possible minimum. Okay. Oh, min does seem reasonable there. Change range dot first minus. Let's see. Min. What should that be? So I guess the range that's coming up is 5, 5. The range we're looking at is 6, 6. So you can't get bigger than the current. Oh, this one looks. 5, 5. Maybe I did. Maybe. Still up at 0, but that's because we haven't actually checked the case. If ranges of u dot second or first. So if you can't intersect, we know the maximum plus minimum, which means you have to be at least less than the maximum possible minimum plus d. This would be that. And symmetric. Zero. You know, that's a good sign. So we pass this to sample, and there's only one sample given, the other one's just the same test case with b set to 1. Well, given that USACO contest, like we're not really worried about wrong submissions, and there's no harm in using the judge to help. I'm actually not going to take the time to debug it, and I'm just going to see what the judge tells us. Well, that's not particularly great. Which cases have b equals 1? Okay, so it passed the test case. These 2 and 4 have b equals 1, so of course they're wrong. Why is it tealing so badly? Our runtime here is actually just linear times the factor log 10 to the 9. Maybe we're not supposed to binary search. Well, I guess we can, maybe we can derive the values of d as we go. And at the end, check if, yeah. I guess we probably can't binary search. Okay, so we don't binary search. Let's just see. We can take the time to design it, but actually, I feel like for this problem, it's really easy to like get off at 1 and like not get the conditions perfect. And it's actually, yeah, I mean, sometimes it's not better to code right away, but here I feel like it's very easy to not know exactly what put in the conditions. So actually, it's kind of easier when you can test it. So sometimes it's not a good idea to code right away, but I am going to modify this to a non-binary search version. Where you can instead keep track of like the best D we saw so far. So I guess we want to start it at 0. So we want to find the maximum it can B. DFS 0 and then CFS. Okay, so we're gonna write a DFS that is not. So I think the base case can still be the same. I think this code is gonna look a lot similar, like very similar. My first intuition for this problem was like, why not binary search? Because like you imagine it can't hurt with the bounds. You're just like, well, it is something that's monotonic, but maybe we're not supposed to binary search. Loop over all the children again. I think this will be the same. There's really no dependence on D here. I think we can keep the same kind of method. So we need to update best D. I think kind of mirror the conditions before if CH range dot first equals max best for that. So that would count for the D that would make sure that would always be valid. And then if so D has to be less than D dot first minus CH range dot first. So it has to be, oh, it has to be like greater than equal to that. And then and I guess we can do the updates again. Something like this. You don't have the distance anymore, but I wonder if we need that. We can just range. Actually looks a little simpler. Actually works. Maybe we just need binary search. Let's try this. So last time we only passed 2 test cases. Hopefully we'll pass some of the other ones, like test case 5, 5, 7, 8. We should pass, yeah, there's 10 of them. So okay, it's 8 test cases total. It's not bad. So I think we just need to do the assignment, which we didn't even think about actually. But I wanted to make sure this text was going to work. So actually, I think it was good to code because you could keep thinking about how to extend this to get the assignment, but then it's good. It's not. It's nice to verify that we had something that works, and half the test case is actually pretty good. This is also probably the point where I would consider switching problems, just because you can think about this in the back of your head, and you don't want to forget the other 2 problems. But we do have 4 hours and 15 minutes left, so I think I'll try to keep working on this one because I feel like there are some ideas here. I guess. Okay. Okay, right. But like once we have whether it's possible or the D that did it. Okay, so once we know the value D, how can we assign them? So if we know it's valid, we know at the end, we know, well, the thing is, the thing we're returning this, like the variable ch range is not range of possible values for each node. And the thing is, you can't decide for a node lower than the root without knowing the root, because, or like your ancestors in general, because this, even if there's a compatible value with this and everything below it, there may be compatible with this, but these actually have to also be compatible together. Like not anytime it works. You actually probably have to do the assignment down. So the idea I'm thinking is 2 steps. One, for each node, consistent with subtree. Then if we do that, we can then do a top-down greedy assignment. You have to like go root down. So pick any possible value compatible with ancestors, which are already chosen, and entire subtree. So I think we're going to need to do 2 DFSs here. A lot more code actually, but that might work. So let's see. Actually, the DFS for the possible ranges might look a lot like this. So maybe it's worthwhile uncommenting this code. We don't need to check if it's valid. We know it's valid. What we do want to do is we want to compute possible ranges. So this DFS this one we want to given this D. So we need to store these somewhere. Ranges. Okay. So the possible range would be max of the left endpoints you can pick. Or like possible ranges that are as like, because you're always going to pick the maximum possible minimum for all the ones below and the minimum possible maximum for all the ones below. Like, you're never going to like spread them out arbitrarily. So I think this possible range, given that we assign the subtree with CH range, I don't know if that makes sense. So this should always have, oh, it's messed up, right? Of course, it's about putting, or we can output if B1, we also want to do DFS. We need to rename the DFS. I do need to copy their input so we can test this. And this, wow. Oh, because we did not read in everything. I guess we didn't really need to recompute this stuff. Like CS range, because, well, I guess now it changes because we now include the minus t and plus t. Maybe it doesn't work. Let me. Useful. Yeah, that's not correct. What if we want minus d and plus d? We should see that the root always has a valid range. That doesn't seem, that can't be right. Okay. No, it would be second minus and first plus, because you can't be too far away from the maximum possible minimum and possible maximum. There we go. So we see that the root has to be 5, 5, 6, 6, and 3, 4. So I guess in the first test case, you can pick either 3 or 4, but the other ones you can't. I don't think it matters which ones you pick in any case. Yeah, if this one's 3, you can only, yeah, it doesn't matter what you pick. Okay. So I guess, yes, okay. I think we can just greedily assign these. So we're gonna need to write a third DFS greedily assign. This one needs to 2. We need to know the minimum above us. We'll just store the final answers here. If you those of you could be the, oh, I don't care. Okay. Do you want to loop over children? To I need to figure out what value to pick. So the possible range is going to be you have to be close enough to the oh yeah, you have to be well, and then positive u dot first probably, and then above dot first. Actually, what value do we get there? Maybe we need a special case for the. We also forgot to store this. That. Okay. And then we'll use that here. Changes. If u equals 0, can't use the above thing because it's not set. That. So the value we assign just be any value in this range. So pick any value in range. So here we compute range. So this accounts for both the subtree and the things above because we already. Above that first was min, above that first that was u. Max, above that second value. The minimum and the maximum, that's t above us. And that should do what I want. Let's try running this. That can't be accurate, but well, I think it's because we never did it here. It can be anything, be consistent with the subtree. It actually matches exactly, even though there's more than one answer, which is easy to check. Let's try submitting this and cross our fingers. It's a good sign. Okay. Seems to be going well. And runs in plenty of time. Okay, so we're one problem done. We're an hour in, so that's pretty good. Of course, if we spent more than like an hour and a half, you probably want to move on, no matter how tempting it is to keep coding. Which one do I have to think about? Let's see, apple catching. Okay, so one thing is that you should notice, and even if like this is not the solution, this is a matching problem where we want to pair up the cows and apples where the edge is there depending. So you have like apples, cows. So, and you want to. So one way you solve maximum matching in a bipartite graph is actually by making a graph and using like network flow. This is the first thing I thought when I saw this problem. However, the important thing to note is these are O of n squared edges. So even though max would work. It's too slow. You need much less edges. So it's not going to work. Some other things. You could try, like if you didn't have the times, right? If you assume no times, so instead you just have positions. Then you could greedily assign left to right by positions. The reason this works is because if there's a cow to the left of you and you have some apples, right, and you're the first apples, there's no reason not to use the cows to the left of you, right? Because they can't be better used for something else. But that doesn't really count on the time. So, like I said, if there's only positions, then it's a meaningless problem. Okay. Maybe you have to have other restrictions. Maybe the restrictions on like the distance between them or something. I don't know. You'd have to theoretically change the problem. So like plus max walking distances. So maybe if all the cows came down at the same time and all the apples came down at the same time or something. I don't know. You could also try doing it like forward or backward in time. So maybe try by of times ti. So once you get some apples, there can be some cows already landed that can reach, or I don't know how the cows arrive, whatever, they just appear. You have some apples and you have some cows that are there. Depending on the time difference, these cows could have different ranges. The thing is, which cow would you pick? It's not obvious. And you don't necessarily always want to pick the leftmost rightmost because you could find a case where like maybe there's more apples here and more apples here at a future time. You would not want to pick the wrong cow or set of cows. Another thing we can try if we try actually, let's make this the times and this the x's. If you have like apples, a cow can reach a set of positions that increases over time. So this is your cow. This increases over time. So the cows would create these like cones. And you would like to assign the apples in, if you want to know which cone to assign them to. If you do it in order of positions, is there a way to know which cow to pick? Like, would we want to pick the cow that has this position? Like if we look at this vertical line where the apple is, if we pick based off where these cows intersect, does that give you an optimal solution? Those are supposed to be right angles, even though I don't look right angles. You would want to make sure you don't take a cow that's usable later, but if we're going by positions, this one feels like if it's usable for an apple later, it should also be in here. Although I guess that's not necessarily true, is it? well, it is here. It's also a drawing. We come up with a case where you want a cow, apple, yeah. So if you had an apple here and then an apple here, we might the wrong cow still. So another thing, what if we try rotating it? Because in this case, like these cones, right, they're just 90 angles. What if we tried rotating positions? So that our cows are like this. And then we run into apples. We want to know, is there a cow which cow do you pick? So maybe you can do like a sweep line here. Maybe after rotating. So we did a sweep line after we rotate. We'd be looking at like an apple. In this case, all the cows we already have, right? If we already added this cow, we already added this cow, you might as well pick the cow with the largest Y, because later on, there's no apples to the left of, I guess the key condition is no apples here. So you pick maximum Y, where these are like X, Y coordinates, but I didn't define how to rotate them. So I guess if we were gonna write the conditions for a cow, when in a cow reach an apple, you want Xi minus Xj is less than or equal to Tj, apple J, cow I, Tj minus Ti. So the cow is at I. Would be equal to. I guess another way to write this, because it's split the outside value, but if you do Xi plus Tj minus Ti, this is the maximum X you can reach. This has to be greater than or equal to Xj. And then the minimum X you can reach is just the time in reverse. This has to be less than or equal to Xj. So we rearrange these, should get these rearranged to give us Xi minus Ti so they have to this quantity, great the quantity for the cow, so you get the quantity of apple. So, and I guess, yeah, this corresponds to checking whether you're within, like, this corresponds to rotation, right? So, you could try to probably prove that like this sweep line works by just looking at formulas, but it's much easier to visualize. And then the formulas for rotating can actually just be these. So this would be one of our X coordinates, to our Y coordinate. And I guess let's make this our X coordinate and this our Y coordinate. So we'd like to do it in decreasing X. And you would like the maximum Y that still fits, right? You do it in decreasing X and you want the max Y, which works. So this seems like something in code. This is actually a pretty standard kind of thing. I think the trick here is just noticing you can rotate it and just I mean, that became clear once you draw it out and you try visualizing it because it wasn't obvious right away. So we can try coding this and see how that goes, or we can think about the other problem. I guess we can try to code this. Right. Template. Okay, so we do need to take in the input. Make a struct to represent a event. Either cows or apples. So in this case, we want to store whether it's apples, the time, and the quantities. All this. Constructor might also even want to store or x and y coordinates. We'll name A and B. So we said we do x being x minus t, where A will be x minus b and b will be x plus t. And we're going to need a comparator. So we said we sort them by decreasing x. A and B are rotate coordinates. So we'll take in there's no default constructor. Just ignore that. Okay, so event qtxn. We want to actually call the constructor, so we do. Sort events. Sweep one. Sort points. We're going to keep track of our current cows. We need a struct for this. So we just need the y coordinate and the amount. So we need to sort them by y coordinates, though, still. Okay, so now we can actually we'll loop through all the points. If points of I that q equals 2, this is if it's an apple. Otherwise, we want to add it to our set of cows. Q. So we know the quantity we want. We'll keep matching with cows until there's no more cows to match with. We can do this using we want upper bound, we want the y greater than or equal to it. So we would like upper bound to he doesn't like that. Okay. Oh, because we're going to have to create a cow to pass it in, but it doesn't matter what quantity we give. So, okay. So in this case, our cow will be that. So if so the amount we okay. Q that will take or matched the min of the amount available and the amount we need. So Q minus equals matched, and if Q equals 0, break. We also need to C dot Q minus equals matched. If C dot Q is 0, we want to make sure we just use the iterator because I don't want it to make it into. So we can't modify it. Okay. So it needs to be deleted if it's less than or equal to Q. In this case, current erase it, else current instead will current insert. How something like that. Subject Q equals 0, we break. Also break there. Okay, we do need to keep track of so int total 0. I guess what's the maximum value? So 10 to the 3 and 10 to the 5 cows, so total should not exceed. Let's see if it compiles at least. It does compile. I guess I do want to do it minus minus because I want less than equal to 0.5. That maybe we dereference the end or something. 1. Okay, no, that's not good. See which cow actually got taken. I guess 6, probably this one. We added. They should not have a value q equals. Oh, yeah, because q is not the quantity. I guess for some reason I was thinking that meant quantities. I think everything's fine. This just needs to be an n. I use q somewhere else too. I'll keep q, but rare one. Okay, so you can see that the 2 cows are added, and for some reason we only matched with one of them, the 5-6 cow, which is this cow right here, and it didn't count. Again, this should be n. Oops. So we can print out which apples are being matched. Okay, that seems. Do any of them actually have a -6? Doesn't seem right. X minus t. Where'd the oh yeah, this one. So of course that one has the lower x coordinates. We're gonna process it first, but we never hit the other apple. That's weird. Okay, why do we miss one? Just don't see one of the apples. I'll just be hear the background noise. That's from the street outside, so I can't do too much about it. Oh, sorry, we do hit all the apples, but for some reason. We did them in order of decreasing x. So for some reason, the one with 7, we didn't match with anything. Why is that? Well, none of the cows were at that point. So maybe we messed up the order we process these in because that should be reachable. Okay, so what did we write? We wanted decreasing x. I guess the issue is there's probably a tie, and so this cow is getting added after, even though it is a cow. We want to put the cows first. So we can wrong. Oh, also, we're supposed to be using the A and B coordinates. Oops. So there's at least 2 bugs there, and we get 9. Is that correct? That's not correct. Just a second. Okay, sorry about that. I'm back. Oh, sorry, this should be if A equals. A, probably still not the bug though. Makes it worse. Okay. So both cows get added first, which is expected. Then was 6, then there was 5. So you can see that was added. This one's impossible. 7 to 18. Let me actually see the audio settings. I hope that's not picking up too much background noise. I don't think it actually is. I don't know if you guys can hear it, but it's pretty loud outside. Okay, so what are we looking at? I probably use my headphones to minimize the audio. I don't know. I'll just leave it. Okay, so we want, I don't see the bug. Okay, what exactly is happening? So we're matching with the 6, 11 cow, which is this cow. We match with all 6. We delete it. Right. We have 5, 6. We match with 1. We update it and reinsert. I'm guessing the issue is our reinsertion didn't work. We'll store these in temporary variables. Then erase it and then that actually, okay, maybe I should have erased it first. I'm not sure why. Let's try another sample. That's the first sample. And then the second sample, we do actually get 9. So let's just try submitting it. Again, there's really no harm. USACO contest to just use the submissions. Oh, it's a good sign. Oh, hmm. Weird. Why would it fail on those test cases? It passed so many. That's probably a good sign that it's a small bug and not something more major if we're only failing on a handful of test cases. But I don't. Okay. I guess one thing when we inserted here, this is actually causing issues. Why was that? It might be because it wasn't actually inserting. I guess what we can do is put that back. And assert and see what happens. Just fail the sample. Oh, this fail on the server. I think I have an idea what the bug is. I just want to see if it'll fail. Just double check. We probably have to make sure we deal with duplicates in the set properly because we're comparing only based on the y values, and the y values can be duplicated. Even if we're told all the points are distinct, x plus t is not necessarily distinct. But it didn't fail the assert. Well, maybe that's not the bug. I was just thinking we might change this to a multi-set, but that assert didn't fail. Maybe we can try it with the multi-set anyway and see what happens. Oh, well, that is the bug. Why didn't the assert fail? I guess it could be failing down here too. It's probably down here that it failed. Oh yeah, because here we're up. That's never gonna fail, right? Because the one that duplicated, we inserted like this is much less likely to fail than this one is. I guess it's not impossible for that. Well, it can't already have a duplicate, so it can't fail there. So yeah, it was never gonna fail the assert. That was a bad assert. But that is the second problem. Now we just have pair programming, which we haven't actually thought about much at all yet. So let's get thinking about it. Let me pull notes. Okay, so the last problem we have is pair programming. So I think we'll just take a minute to read and think about this again. I guess let's look at one of the samples. I guess we have like 0 and 1. And I guess 0, 1 doesn't matter what do you put them. So zeros actually eliminate a lot. So 0, 1, you only have the case. Like those are both equal 0. Let's look at 1, 2 plus 0, 2. The thing is that I notice here is one observation, zeros, lock, all previous, characters from having any effect. So it's as if you never had the program start from there. So in this case, we can actually ignore the plus, right? This is equivalent. I guess the 0 could block out parts of the first program. Like maybe the 0 is inserted here. And so it blocks out those. But let's assume, so sometimes for problems, it's useful to try to assume something where, let's try a simpler version. So assume no zeros, because I think we can see how to deal with them. We probably have to like sum up the answers for each one. Also, the bounds here ends up to 2000. So because we're given two sequences and you want to know how many programs can there might be some sort of like n squared dp. That's my first guess. So we're going to assume no zeros and see if we can still come up with a solution. So sometimes just having wishful thinking or eliminating a part of the problem makes it easier. And I guess here, another observation. Ones have no impact on the result. They can be placed where they don't change values. So we can, this implies we can move all ones before choosing answer. Okay, so those are two observations. Let's make it a bit simpler because we eliminate ones and zeros and we're left with just operations of another digit or plus. So I guess, how do you, yeah. We're also, another thing important to note, yeah, we can see note, yeah. Okay, so the other thing, note all must be distinct. So I guess, the kind of DPID we might be looking for is like, DP ij equals the number of distinct solutions using A, but starting at I, and B, but starting at J. So this is a pretty standard formulation for this kind of DP problem. The thing is, there's more than one. How do you not double count? I think, because like when you have a sequence, like for example, this will double count. We want to watch out for double counting. So if you have like plus, 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 plus 2, I don't know. You can put those 4 pluses in any order, right? You don't want to pick this plus is not different from this plus because plus x plus y is equal to plus y plus x. So if there's multiple pluses, need to treat all pluses as identical. So in that case, with the plus, 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 plus 2, you can either get plus, plus 2, plus, 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 plus 2, plus, or plus, 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 plus 2. So maybe we want to do like an O of n squared states, and we have like an O of n transitions, where you either you force yourself to take the 2, but you pick how many of the ones to take. So you loop over 2, 3, and 4, and you take that many. Thing is, this is too slow. But maybe we can add another data structure. Because in this case, we're probably gonna be summing over like a consecutive sequence. We would be summing over this implies we could use like any sort of like range sum structure, or just prefix sums, basically just another DP function. We just compute the prefix functions in the table and look those up instead. And so we can actually avoid, we can ask for like, given a fixed I, a range of J, or given a fixed J, a range of I. The other thing to note, order of digits, except for one, except 1, 0, one another observation, does not affect the result. So, times 5 times 6, this is equal to times 6 times 5. Assuming you have something before, right? You have to assume. Oh, I guess, yeah. Digits at the start don't change any result. That doesn't mean we don't want to exclude them though. I think we want to include them. They don't change any results. So I guess, well, we do want to deal with these cases, right? So this is one of the cases where we want to force ourselves taking our pluses. We could like force ourselves to take the 2, but then you also worry about what's there. And I think it'd be easier to make our DP state something like this. So a potential DP state can be DP I J as before, and now we include, let's just say K, where K equals whether to use first character from A, B, or neither. Because at the start, you would want DP 0, 0, 0, where maybe K equals 0 implies neither, 1 implies A, 2 implies B. This would be our answer. I don't know. I guess we're at the sums, but maybe we can try something with the O of N transitions. This might work. The order of digits and the order of pluses don't matter. So you can actually treat all digits the same and all pluses the same. So it's just 2 types, and you're just asked to like interleave 2 binary strings basically. Except there's the case with 1s and 0s. And 0s add quite a bit of trickiness. 1s are actually really simple to deal with. We just remove all the 1s, and that's the simplest. So we can start by coding this and see how it goes. Bigger. Okay, so I want to take in what we have is we have the length. We want these strings. I'll just call it A and B. Okay, so we want to remove all 1s. So we can have this function that's remove ones. Yes, this is a very simple function. In this case, res plus equals, sorry, 1. Let's just say 1. I guess we also want to remove zeros, but let's just test it without. Let's just do this. Okay. Okay, so once we do the processing there, then we'll want to talk about those. I don't want to create a TP table to work with. We'll keep track of 3 values. So we'll construct our TP table. We'll do it backwards. So we'll start from I equals a dot size I greater than 0, I minus j dot size b greater than equal 0, j greater than equal to 0, j minus. That should be capitalized. And then I don't think it matters before we do k in. K should be. So we want the table to go in reverse order. So what's our base case? The base case is probably if I equals a dot size or j equals b dot size. So in this case, dp I j k equals 1 because there's just one state. You take everything in order. Else. So in this case, if k equals 0, I guess another thing we might want to compute is we compute next different type of character. So what I mean by that is like when is the next non-plus if you're on a plus, and when is the next non-digit if you're on a digit. So we can do this recomputation. We'll do it first. So if I equals a dot size minus 1, or a of I equals plus not equal to a of I plus 1 equals plus. So if it's a plus on only one of them, then last of I plus 1, else next a. Like that. We can copy this. The indentation. Better. Okay. And then we want to change this to B, B, B. So we'll need this in order to do our sums, I think. But I guess we don't actually need this yet. So actually, no, we do need it. Int possible a is equal to next a of I minus I. This shows how many like available pluses on each side or how many available digits on each side, because we can order them in any way. We want to sum them up. Int mod. Okay, so we're not forced to take one of them. Take any number I just need to make sure to initialize it to 0 plus dp I plus L j plus pos b. So we're going to take all the ones on B, but some number on A. And that would give us, and we want to force ourselves to take the B one, so we don't just double count. So by saying 2, we should not double count. I guess we can include, yeah. We want to be able to take all. If we take all on one, is that actually appropriate? Take all on one, you should now. No, that's not appropriate. I should not call it like that. Force ourselves to take the A character and then dpijk mod. Or either take both. Take both, you can take either character first. A plus B 1 mod, and we'll just copy this in order to do it the other way. Well, I guess I could make both those loops up to, yeah, whatever, it doesn't matter. I should kind of do, so this is the needs to be replaced. Prefix sums. When we're trying to do a problem where we're not even certain the DP is correct, or we're not certain there's no bugs, it's probably better to code the least complicated version and just check that passes first before adding the prefix sums. So I'm not going to add the prefix sums right away. Well, how do we do the case where if we're forced to take the first character A? I guess we should make these cases more like matter. Thing is, yeah, actually, maybe another way to formulate this, instead of I might change this to where instead of this just says take a digit first or take a plus first. It can be our last condition. Because then what we can do here, you don't have to count for K, we can just say take a different type, but I don't care which part we're on. And then so make sure we don't want to count, we'll make sure, or we don't undercount. There. Otherwise, we have a fixed K, so we have to take A of I is the correct one. B of I is the correct one. We take just A of I. And we don't have any restriction on the next characters, so we can do I plus J. We'll do the same thing for over here. But instead of I plus 1, just do that might work. Let's just change the answer. dp000 plus dp001. You can start with either a digit or a plus. The chance this works is probably pretty low. Of course, we're still missing stuff. It does not like the recordings. Let's take the input. Wildly off. Let's try printing some. Okay, just a little complaint about initialization. Okay, so 1, 0. Well, there's no character, right? Oh, we didn't process the zeros. That won't work. That won't work. That won't work. Only test case that works is the last one, and that's the biggest one. Okay, that's not great. I think our base case is also wrong. If DP, or sorry, if I equals in a dot size and then j equals and dpijk equals 1. Otherwise, you have to actually make sure the type matches. So if I a of I, like d of I equals plus. So if the correct type is 1, otherwise it's 0. I lowered the answer quite a bit. So at least that was counting invalid cases. Here, I think what we should do, if C not equal to 1, we'll reset the string. So we'll remove the zeros, but we won't count them. But we can keep track of that they are there. It's just reverse negative. Yeah. Okay, for 1x. So we get 2 on the first one. There should only be 1. The strings are empty. So it seems like for the last case, well, if you are, okay. In this case, it makes empty 1, maybe. Now the last case is severely overcounting. The other one's actually closer. But oh yeah, this one we don't even count everything. So it should undercount, and it's actually getting the correct answer, which means something's wrong in the last test case. Is way too large at 45. So something's going on here. Hmm. Okay. Am I missing anything? I don't know. Something going wrong. 45. It's really hard to look at this and debug it though. So don't know what's going on. So we're very much over counting. To make sure we reset everything. Yeah, well, 4, 3. Let's put out A and B. Try to look at these. If I take a digit, you have to take, okay, 4. 4 is out of bounds, 3 is out of bounds. The answer is 1. Okay, that's not surprising. That's the base case. Also 1 here. Does that matter that it? Actually, that might matter because I think we're double counting here. Whenever. Hmm. This might be double counting. It's, if you reach like the end, then you get 1 on both and you double count. So how do I fix that? I don't know. I don't know there. Oh, well, that can't be out of bounds. That can't double count. It's only double counts if both of them are out of bounds, but because we fixed that here, this can never double count. Okay, that's fine. That can't be an issue. I guess we didn't check if we're actually on the right type. Here, this should be. It shrunk once more, but the answer is 9. That's one thing. It should be set to 0 in the other case. You'll always use the default case. So that got smaller. 18, 33. 3 is close to another one. 33 is a little large for this one. It should just be 9. Okay, I don't see it. I don't see the bug. What else is it? What's the output in the other cases? One. No, 2 plus. Here it should either be 2 plus or 2 plus 2. Those are my choices. So we should get 2. Of course, the answer is 3 because there's another case that's not being considered. Because of the fact that we don't process zeros, but in this case, we should get. We'd expect DP 0, 0. Okay, so let's add this output and bug the small case because we know the small case is wrong. So 0, 0, 0 should be 2, right? Instead it's 1. 0, 0, 0 will match this case, right? We'll do a loop. So we would loop over. You take just the right. Take both 2s. You get to 1, 1, 1, 1, 1, right? Do only 1, 2. You have 2 choices, right? Because you either do 0, 1, 1, 0, right? Or you 1, 0, 1, which is 1. Seems correct to 1, 1. Maybe these loops aren't complete. Oh. I don't think we computed these correctly. Oh, these should not be else's then. Okay, so those were not being computed correctly, and so maybe not, but nonsense. 2, 3, 20. So it shrunk yet again. And now it's at 9. I want to get to 9. Is 3 correct for this one? We either do plus plus 9 plus 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 plus. Yeah, there's 3. Okay, so the only test case which doesn't do what we expect, not that it's correct, we haven't considered zeros yet, is this test case, which is just wrong. But why? Weird. Okay. It's hard to debug this though. Where is it likely to be? Hmm. What else we can actually see what this slide there? 2, 0, 2, 1. Seems reasonable. 2, 2. Wait, 2, 1. Okay. Actually a J. I got worse again. The cases are wrong. Okay, so I have a smaller case debug. I had a typo there. I's and J's are pretty similar. 2, 2. You know what? I made that typo in another place too. Okay, that's a good sign because the last test case actually doesn't depend on zeros. What do we get now? It's closer. We have 1, 3, 9, 9. 1, 2, 3, 9. So these are actually the answers we expected. I think in order to deal with zeros, we need to we want to loop over all possible positions for E. All the way up to we'll do nth equals nth plus dp 0 I 0 plus dp 0 now overflows. That's not good. Why does it double count? I guess it's because like digits at the start don't count, right? So when you cut off a 2, you might as well just not use the 2 as well. So maybe we should make ours specifically start with a plus. We have to pick like how many go at the start. So I think we might want to have to do a special case in order to handle digits. Kind of want to combine these. So what? I guess first a equals a dot prime plus. Wait. I want you to start. Actually, I guess I want a dot side. B dot prime plus first plus not equal to -1 first plus. Rename all these. Make these not. So A is the 0. This would maybe work. Well, it's actually, it might work. We force ourselves to start with a plus always. Take the sum in order to figure out how many to exclude that are not pluses. Closer. That one does have a 0. 0b, so we loop over. It should be 0, I guess. I got worse. Oh, this should be 1. That's there. Okay. It should be 0 instead. Oh, what did I put? Out there. I don't. It's supposed to be 3 because you have 2, 2 plus 2, and plus 2, 2, which we're missing. Yeah, let's add a little output to help us. I and j. Okay, let's see. 0, 0. I feel like that shouldn't be. Well, yes, it should be 0. So we include how many digits to cut off here. There's only a 2, so we tried. I guess 2, 0 should actually. Where do we get 3 though? Here we can see that 0, 0, 0 gives us 2. Okay, fair. That whether you include it, include 2 doesn't matter, but that should be 0. 1, 0, 1 should be plus 2, and I have to start with a plus. Does in fact only if you want to do it. Yeah, if we're not including. Yeah, that shouldn't have been 0. My bad. 1399. Well, correct, isn't it? So some more output. Try saying this. Seems like it could. Obviously, we're not done because we still haven't implemented the prefix sums, and we also might have other bugs. So let's see how we do on this problem. Well, that's not good. One thing I do want to check though is of course it's possible in both def zeros. I'm just curious, how many test cases do we fail? Because that was probably something we didn't address. So at least tell us, are we on the right track? Because if this gives us runtime errors on the ones that we fail, that's probably the reason we're failing. That is a good sign. So I think what we're doing here, we also want to do int otherwise first. That's not good. Worse. I wonder how that started causing a runtime error there. Wait, maybe I need to put parentheses. I would be surprised if parentheses did. I guess because that if statement never runs. Fair. That's not good. They really should warn me for that, sadly, but I didn't. Okay. Good. They're still wrong. Because we might be double counting though. So I think what we might want here is I less than one of them. You don't want to double count on both if you're looking at this. You don't want them both to be past that. Okay. So then how many test cases locally that have that example I'm just resubmitting to test it. Let's see. That is a good sign. Okay. So now we just needed the prefix sums. This is cubic. Okay. We actually got most of the test cases for having something that's cubic. I guess, did they list? Yeah, I mean. Okay. I guess they want that. Okay, so we're gonna want this is the code we need to change. And here we need to actually update these. rpref ij k equals rpref I plus 1 jk cpref I equals. I guess add it to our prefix sums. Now we should use them, which we don't need the for loops anymore. We just need dpijk equals dpijk plus rpref ijk. I think no, I j plus copy 1 minus k mod minus r pref I plus a 1 is 1 minus k. The only difference here is we just want to make this one I plus a. They should be C pref. See if it still works. It does still work, which is a good sign. I don't know. We'll submit. It wasn't too hard to change, I don't think. So let's see if it works. And there we go. Okay, so that was the last problem. This was a fun contest. It's reasonably challenging. I feel like apple catching is probably the easiest one in the end. Like sweep line's pretty standard for gold. So if you haven't seen sweep line and stuff, it's something you should make sure you know. This one, it's unique, but it's tricky to debug and implement. So actually pretty hard. And then this one, honestly, the solution for me is still pretty unintuitive here. Like I got the idea, I was able to implement it, but like we had a lot of bugs in this one. So this one's also kind of tricky. But yeah, that's the entire contest. Hopefully this gives you an idea of what it looks like to do a gold contest, implement the problems, how to approach them. Hope you guys enjoyed this. Thank you guys for watching though. But that's all we have. All right, bye.